So now we know that elements were created during the Big Bang. Elements were and are still being created in stars. And elements were and also are being created in the death of stars. So let's take a look now at supernova nucleosynthesis, particularly type 2 supernova. Now in type 2 supernova, the core collapses. So we call this core collapse supernova. And this occurs in the last stage in the life of massive stars that are at least 8 times larger than our sun. So this produces heat. The process, the supernova that occurs produces heat, and the heat also produces pressure. Okay? The pressure created pushes outward against the forces of gravity that pull inward on the star. Okay? So when you say gravitational force, this is the pull inward, and the pressure released by the heat generated pushes outward against the force of gravity. In a stable star, the inward gravity and outward pressure are in balance. As a star burns through its fuel, okay, so eventually when a star burns, eventually it loses its fuel and it begins to cool. The outward forces of pressure drop, and when the pressure drops low enough in a massive star, gravity suddenly takes over and the star collapses in just seconds. Okay? So neutrons bombard the nuclei, and this forms heavy elements. Okay? So what are these heavy elements that are created? You have gold, you have uranium, and this occurs in seconds during the explosion of your star. So as a result, elements are dispersed into space, enriching the interstellar medium. So again, as a massive star collapses, it produces a shock wave that can induce fusion in the star's outer shell, and these fusion reactions create new atomic nuclei in a process known as nucleosynthesis. So supernovae are considered one of the original sources of the elements heavier than iron in the universe. So it's in the Big Bang nucleosynthesis that the smaller atoms are created. It's in the death of stars that bigger atoms are created. More massive atoms are created. So within galaxies, and there are trillions of galaxies in the universe, stars and supernovae play an important role in synthesizing elements from carbon to uranium. So the more massive elements are created in stars and in the death of stars. So we have here from carbon, you have there. So from carbon, so all these elements were created in stars and in supernovae. So only these elements, hydrogen, helium, and a small amount of lithium, and probably beryllium as well, and boron maybe, were created during the Big Bang. This is an image of the Crab Nebula associated with 1054 supernova. The orange filaments are tattered remains of the star. Okay, so this is an image of an exploding star and consists mostly of hydrogen. Okay? The rapidly spinning neutron star embedded in the center of the nebula is the dynamo powering the nebula's eerie interior bluish glow. Okay, so you have here, you will find a spinning neutron star. Okay? The blue light comes from the electrons whirling at nearly the speed of light. It travels at very, very high speed around magnetic field, and these lines from the neutron star. So a neutron star is the crushed, ultra-dense core of the exploding star. So these are the top 10 elements in the sun and their relative abundance. So these are the elements that we find in the sun. The most abundant is hydrogen, and then you have helium, followed by oxygen, then you have carbon, nitrogen, silicon, magnesium, neon, iron, and sulfur. This is a graph showing the relative abundance of elements and their atomic numbers. Again, the higher the atomic number, the bigger the atom is. Okay? So hydrogen and helium, the two simplest elements, hydrogen having one proton, helium having two protons, they were created in the Big Bang. Carbon, nitrogen, oxygen, and iron, they were forged inside stars or in exploding stars. So beyond iron in the periodic table, so those larger elements, atoms larger than the atom of iron, were produced during supernova explosions by neutron capture. In the previous slide, boron, beryllium, and lithium were mentioned. And these elements were created by cosmic ray spallation. Now, what is this cosmic ray spallation? Cosmic ray spallation is a nuclear reaction where high-energy cosmic rays, like protons, collide with atoms in the interstellar medium or other objects, causing them to break apart and produce new lighter elements. In other words, they were created from larger atoms, broken apart by nuclear fission, and then this is how boron, beryllium, and lithium were created. Now let's take a look at the nucleus, because all elements were created by way of nuclear reaction. The nucleus is incredibly dense. It contributes 99.97% of the atom's mass, but occupies only about 1/10 trillionth of its volume. Okay? It occupies a very, very, very small volume, but yet the mass of the atom is concentrated in the nucleus, which means to say that the mass of the atom is dependent on the number of protons and neutrons. Okay? So picture this. If you have a cube, if you have a small cube with dimension 1 centimeter by 1 centimeter by 1 centimeter, that cube will have a volume of 1 cubic centimeter. If this is pure water, if this cube is made up of pure water, it will have a mass of 1 gram. Okay? So we have another cube, same dimension, 1 centimeter by 1 centimeter by 1 centimeter. But it's not made of pure water, but pure gold. That 1 cubic centimeter cube will have a mass of about 19 grams. In other words, the density of gold is 19 grams per cubic centimeter. The density of water is 1 gram per cubic centimeter. Now you have another cube, same dimension, 1 centimeter by 1 centimeter by 1 centimeter. But it's not made of water, it's not made of pure gold, but it's made of pure atomic nuclei. Same volume of pure atomic nuclei, same volume as the water, same volume as the gold. That 1 cubic centimeter of pure atomic nuclei would weigh about 120 billion kilograms. In other words, the density of atomic nuclei is 120 billion kilograms per cubic centimeter. Okay, nuclei are made up of protons and neutrons because the electrons are not found in the nucleus. They are found orbiting around the nucleus. Okay? But the mass of a nucleus is always less than the sum of the individual masses of the protons and neutrons which constitute it. Okay? So if you add the mass of the protons to the mass of the neutrons, okay, the sum is always less than the sum of the individual masses. Okay? The sum is less than the individual masses. Now there's a difference, right? So this difference is a measure of the nuclear binding energy which holds the nucleus together, which means that part of the mass was converted to energy to bind the protons and the neutrons together, given that the protons, they will repel each other. There has to be a binding energy to put them together in the nucleus. Now, this binding energy can be calculated from Einstein's equation, E is equal to mc squared.